last time we talked about the squeeze theorem, where if you have a function bounded between two other functions, we can use that information to calculate a limit. Now, this is a very graphical way of thinking, so I wanted to demonstrate this with a special limit in Desmos. Here in red, I have graphed the function y equals the sine of x divided by x. It's a function that we've seen before. And again, Desmos doesn't draw the hole here, but there is one. If I click on this, you should be able to read there, for x equals 0, this formula is undefined. Sine of 0 is 0. 0 divided by 0 is undefined. That's not a number I can compute. But it does look as though there is a limit. If I come in from the right and I drag my mouse along the curve, my x coordinate is getting closer to 0 and my y coordinate is getting closer to 1. And similarly, if I come in from the left, the x coordinate is getting closer to 0 and the y coordinate is getting closer to 1. But there's a different way to think about this, and that's using the squeeze theorem. So I want to think of two different functions I can use to bound my graph and make it more obvious that that limit exists. Now, this is adapted from the very end of section 1.4 in your textbook. Stuart is doing this with some trigonometry, which is fine, but I wanted to give a different interpretation. So my first observation is, well, the largest this function gets is going to be y equals 1. There's nowhere on this graph where the function is larger than y equals 1. I can just see that from the picture. So I'm going to graph y equals 1. It's a horizontal line. And hey, cool. My function, my graph of the function is always less than that. Okay. So what's my lower bound going to be? My squeeze theorem requires me to have an upper bound and a lower bound. And as those two bounds get closer together, the function that I care about is literally squeezed in between them. Now, again, Stuart gives some trigonometric reasoning as to why the cosine of x will be our lower bound, but I'm not terribly concerned with the trig reasoning. You can find that in the appendix, is where he's sort of thrown that under the rug. But just graphically, I can see that my cosine function in black here is less than my sine of x divided by x, at least in the region where I care about that kind of thing. They cross over here, but that's not important for what I'm doing right now. So the limit of this sine of x divided by x as x approaches 0 is stuck in between the limit of the purple function, but that's just a constant, so the limit of y equals 1 as x approaches 0 is just y equals 1. That's going to be an upper bound for the value of the limit of the red function. The lower bound is going to be the limit of the cosine of x as x approaches 0. And again, cosine of x is one of those very nice functions where I can do direct substitution. So if I want the limit of the cosine function as x approaches 0, I just calculate cosine of 0, which I know is 1. So follow it with my mouse there. I go to 1. Now, I'm going to zoom in to show what's going on in a little bit more detail. This red function is always going to be stuck in between the purple function on the top and the black function on the bottom. So it has no choice but to tend towards the limit of 1. So there's my hole in the function. Thank you, Desmos. My formula is undefined for x equals 0, but in the limit, as x approaches 0, my y-coordinate is approaching 1. And now they're so close together that Desmos can't even render the different colors.